Okay, welcome back to Organic Chemistry 2341. This is section 253, our Tuesday, Thursday morning class at 8 a.m. This is Thursday morning before spring break, so I know some of you cut out early, but please watch this video. It has a lot of information about it, and you're going to need it because we have 3 whole sections in chapter 6. And this is the cool part. This is where we actually get to start to do chemistry, right? Chapter 1, we figured out what bonds were, and we figured out what polar bonds were and the shape of things, right? And then we added acids and bases, and then we figured out how to name everything, and then we got a little deeper into it, but now we get to actually do chemical reactions, okay? So that's where we're going to start doing everything, and this is where it gets fun, and it's where we start. I'm going to show you some tricks to figure out what's going to happen when and how things are going to react, okay? So without further ado, I'm going to go ahead and share my screen and start with what I think is a very cool topic. All right. So what we're going to talk about today is chemical reactivity and mechanisms and thermodynamics and kinetics. Okay, so we're going to get through all of those today, and we will hopefully have a good understanding of what they all are and how to use reaction diagrams to get us to understand what's happening when in a reaction. Okay, so let's talk about reactions first. We're going to have a variety of reactions that we're going to do through this semester as well as next semester. So, but they all fall under these general categories, okay? So I'm going to show you the 5 or 6 things that can happen in a reaction mechanism, but I'm also going to show you these 5 or 6 reactions that you'll see over and over and over again, and we'll see them. And so being familiar with the types of reactions, what they're called, and what their products are is going to help you with all the other functional group transformations we'll do throughout the rest of this semester and next, okay? So the first reaction we want to talk about is what we call a substitution reaction, okay? So in a substitution reaction, like the name implies, is we're going to take one group and kick it off and replace it with some other group. And so we've taken a group and we've done a functional group transformation. In this case, we've taken an alkyl halide and turned it into an alcohol, okay? So the cool thing about that is in these substitutions, there can be either attacked by a nucleophile, which I'll explain later, or an electrophile. In this case, we have a negative charge here. The negative charge is the one that's going to come in here and make that new bond with the carbon. These electrons are going to kick out, and we're going to have our new, hopefully stronger, chemical bond. And that's the driving force for these reactions. Okay, the next kind of reaction we want to look at is, well, if we can substitute things, we can also eliminate things. We can eliminate things from 2 adjacent carbons. Why does it have to be 2 adjacent carbons? Well, you have to put the electron somewhere. And in this case, when we do it with 2 adjacent carbons, we can form a pi bond. So in this case here, we would have, like we'll call this carbon 1 and we'll call this carbon 2. We're going to remove the hydrogen from the carbon 1. These electrons are going to kick in, these electrons are going to kick out, and we're going to form our double bond. So we're eliminating a small molecule, in this case, HBr. Okay, so that's why we call elimination reactions, okay? So the cool thing about this is that you can go from your 1 compound to 2 compounds in the course of the reaction here. And of course, you have to have a driving force for this. In this case, we're using a base to remove an acid from our alkyl halide to create our double bond. So now we've changed the hybridization of our carbons in this elimination reaction. Okay. So if we've eliminated something, well, we can also add to that double bond by what we call addition reactions. But again, it has to add on one atom is going to add to 1 carbon, and 1 atom is going to add to the adjacent carbon. So this is the reverse reaction of the elimination reaction we saw. We can take, in this case, HBr with no other requirement necessary. What's going to happen is the H is going to go one side, the Br is going to go on the other to recreate our alkyl halide. Notice the hybridization changed again. We went from an sp2 hybridized carbon with a double bond to only having sp3 hybridized carbons. Okay, so with that change in hybridization comes a change in shape. Okay, so don't forget that. Okay, the next kind of reaction we're going to talk about is what we call a rearrangement reaction. This is where all the chemical bonds are still where they were, except something has moved from a connection from one way or the other. One of the easiest ways to see this is looking at the rearrangement of an alkene, going from the cis alkene, because both of these are on the same side, to a trans alkene. Okay, now this does not happen without some major force here. Remember that double bond is rigid. It does not rotate there. So what we have to do is use an acid catalyzed to break the double bond, let it have free rotation around that new sigma bond, and reform that double bond. Okay, that's not the only kind of rearrangement we have. We also have what we call a carbocation rearrangement, which we will get to talk about today. Okay, so the next kind of reaction we have is we have bond breaking, okay, or bond cleavage, okay, but it can happen in two different ways, okay. We can have it where we have both electrons leave with one group, and so we end up with a negative charge on one compound and a positive charge on the other. We call this heterolytic cleavage because it's different. They each walked away with different things. One walked away with 2 electrons, one had no electrons left. And so that's a different cleavage, and therefore it's a heterolytic cleavage. That's most common that we're going to see in almost all the reactions we do, except for chapter 10. Chapter 10, we're going to talk about radicals. And when we talk about radicals, we're going to talk about what we call a homolytic cleavage, meaning that they leave with each with the same. And so what they do is they take one electron from, you have 2 electrons in your sigma bond, and they each get one of them. And so they generate a radical or an unpaired electron. So we call that homolytic cleavage. Okay. So heterolytic cleavage we're going to use most of the time. Homolytic cleavage we're going to use in chapter 10. Okay. It's important to note is that bond breaking is a endothermic process, meaning it absorbs heat. Okay, so it absorbs heat because you are raising the potential energy of the 2 components. You're taking a nice stable component with no charge, you're raising its potential energy to give you 2 charged species. So it has to absorb heat, and therefore it's an endothermic process. We're going to talk a lot more about endo and exothermic by the end of this lecture. Okay, so the next thing we can do is we can form a bond. And we can form a bond in 2 different ways, just like we had the heterolytic cleavage and the homolytic cleavage. If we have a formation by a pair of electrons coming in to create a new sigma bond, we call that heterogenic. So we're generating a sigma bond by using 2 electrons from one species and attaching to another species. Okay. Now, in this case, we're going to learn the term electrophile and nucleophile. An electrophile is seeking out electrons or negative charge. A nucleophile is seeking out a positive charge to share its electrons with. We're going to do a lot more about nucleophiles and electrophiles, but I wanted to introduce the topic because it's here on the slide. The other type of bond formation we can do is called homogenic, which means they each have 1 electron each, and they use that electrons to create a pair, which creates our sigma bond. Okay, so we have heterogenic, which we're going to use most of the time. Homogenic happens in radical reactions. Now, if bond breaking was endothermic, took heat to make it happen, when we form bonds, it's exothermic. It gives off heat. It takes 2 high energy components, and by forming that bond, it gives off heat. So bond formation is exothermic. It gives off heat. Okay. Nope. There we go. So we talked a couple about things about what an exothermic or an endothermic reaction. So I want to dive into thermodynamics. Okay. In thermodynamics is basically the change in energy of the system, and we can measure it in a couple different ways. Okay. So there is, the first way we can look at it is the change in free energy, or the Gibbs free energy. Okay. So if you can think about it, is Gibbs free energy is when you have very little Gibbs free energy stored in a molecule, it doesn't have very much energy. When you have a lot of Gibbs free energy stored in a molecule, it has more potential energy, which means that if you decrease the amount of potential energy, you're giving off the Gibbs free energy. Okay. So if you can think about it is, we're going to actually have a visualization using a reaction diagram to kind of indicate this. Okay, so in an energy diagram, it tells us a lot about the reaction just in a visual sense. Okay, on the y-axis here, we have the free energy. In this case, we're showing the Gibbs free energy. It could also be potential energy, okay, or enthalpy, the potential energy of our system. Okay, so and then we have a reaction coordinate. Okay, this is basically the time at which it takes, or the approximate series of events that happens going from two reactants going through some kind of high energy state because we're increasing energy here, and then cascading down to its final products. Okay. And if the final products have less free stored energy than the starting materials, it gives off Gibbs free energy, and it's called exergonic. It's releasing Gibbs free energy. Okay. So in this case, anytime you have the products below the energy level of the starting materials, right here, we have an exergonic reaction. Okay, so that's just the energy of the system, the potential energy of these two molecules and the potential energy of these two molecules and their difference. Okay, so we have to start from our starting materials, go through some kind of state, and then once it does, we formed different bonds, and now we have to measure that energy of those different bonds. And that's what we see in this reaction diagram. Okay, so this is a great visualization of thermodynamics and the storing and releasing of energy. It also gives us a lot about the driving forces for why reactions occur. Okay, so in any reaction, you can write an equilibrium constant for it. So in any reaction, there tends to be some kind of equilibrium. Sometimes the equilibrium is so small, it's negligible, and you don't even see the other products, but technically, all reactions can be forced to be reversible, okay, if there's a driving force. So when we're talking about that equilibrium constant, or that wherever that equilibrium lies, we have to measure the concentration of the products and divide that by the concentration of the reactants. Because in theory, you're driving the reaction to products, right? So you want to divide the products by the reactants. And in this case, C and D are the products of this reaction. A and B were the starting materials. So it's the concentration of C times the concentration of D divided by the concentration of A times the concentration of B. And that gives a measured equilibrium constant, okay? But how does that relate to free energy? Well, we have an equation here, okay? That equation is that the equilibrium constant right here, if we take the natural log of it, multiply it by temperature in Kelvin, and we have the ideal gas law, we're going to get the change in Gibbs free energy. Okay, so we can actually measure the change in Gibbs free energy by knowing our equilibrium constant, by measuring the concentration of these species at equilibrium. Okay, so don't worry, I'm not going to make you do the calculation. I just want you to know the Gibbs free energy is actually a measured number. It's not this mythical thing we just make up. Okay, we do actually physically measure that number. Okay, so I said that a lot of times we're also looking at the change in the heat of the reaction, okay? And we call this the change in energy, or the change in the bond energy, enthalpy, okay? And Gibbs free energy is related to enthalpy. And most of the time I'm going to use the change in enthalpy because that tells us whether we're giving off heat or absorbing heat in our reaction, okay? So the Gibbs free energy is related to the enthalpy of the reaction, or the change in heat, but we also have to take into account the temperature, again in Kelvin, and the change in entropy. Okay, entropy is a measure of disorder. So if you go from one thing to two things, you've increased entropy. So that's what the entropy component. So there's this change in entropy. Tells you if you go from one thing to two things, you might have changed that Gibbs free energy, that total energy in the system. That's why it's a component. Most of the time, temperature and the change in entropy is small enough that we can say that the Gibbs free energy is approximately the change in enthalpy. The change in Gibbs free energy is approximately the change in enthalpy. Okay. It's not identical because we do have these two other components, but there is a time where they become important, and I'll talk about that on the next slide. Okay, so in general, a spontaneous reaction will occur if the process gives off heat, okay? If the process gives off heat, that makes it exothermic, okay? So exo meaning gives off or out, and thermic meaning heat. So if it gives off heat, it tends to be spontaneous. And it also becomes more disordered, okay? If you go from one product to two, or you do some things like that, you can increase disorder, and therefore you have a spontaneous reaction. A spontaneous reaction will not occur if the process increases the enthalpy, i.e. you have to put heat into the system to make it go to that new product, or you decrease the amount of entropy. You go from 5 things to 1 thing, okay? There has to be a driving force for that. If you're adding heat and changing entropy at the same time, and they are both increasing, the reaction will not occur spontaneously. You have to use some other way to do it. Okay. Now, there are some things where you look at, okay, well, if the delta enthalpy or delta H is the dominant factor, we can see that in low temperature reactions below 500 degrees Kelvin, typically enthalpy wins, okay? Enthalpy is more important, okay? With temperatures above 500 Kelvin, we have to start thinking about the entropy component, because the entropy component is multiplied times the temperature. So even though the entropy component is small, by multiplying it times the temperature, you can actually start to dominate the reaction by that change in entropy. Okay, there we go. So when S is greater than 0, the reaction is favored because of the increased entropy. So if you're going from 5 things to 1 thing, and you're doing it at a very high temperature, entropy is dominating your reaction. Okay, so we only have to worry about the entropy component when we have let me just go to the next line here. Okay, so when starting from a single material that forms 2 products, you have increased entropy. You went from 1 thing that has a certain amount of freedom or disorder, and you turn it into 2 things. Now that's more disorder. You've doubled the disorder, okay? The other thing that can increase disorder is if you have a ring, okay? Remember when we had rings and we had only a few configurations that we could have on it? By breaking that ring and turning it into a linear chain, now there are many more conformations. You're increasing disorder. So entropy is positive when you break a ring and turn it into straight chains. Okay. When entropy is negative, the reaction is not favored because of the decrease in entropy, unless there is a lot of heat given off, or a negative delta H. If you give off a lot of heat, if the heat is exothermic, the entropy component is not as important. In many reactions, we start with 2 reagents, we go to 2 reagents, and so our change in entropy is not very high. That means the enthalpy is the most important thing. Okay, so when we want reactants to be favored or stay unreacted, we want our equilibrium constant to be less than 1, meaning that you have more reactants than products, right? Because it's the reactants are on the bottom of the equation. When your change in enthalpy is positive, when you have to put heat into the reaction to make the products, it would rather stay as the reactants. When the Gibbs free energy is greater than 0 or positive, that's also, you have to put energy into the system to get to the products, and it's not favored. And when entropy is less than 0, then you have you are going from 1 thing to 5 things, 5 things to 1 thing. It's also not favored. But that means the opposite is true when you want products. You want your equilibrium constant to be greater than 1. You want more products, which are on the top, than reactants. So it's bigger than 1. You want to have a negative enthalpy. You want to give off heat. You want to give off Gibbs free energy, which is this next component here. And if possible, again, entropy is not the most important thing if you're giving off a lot of heat. You want your entropy to be positive. Okay, so what does that mean? It's really hard to remember. Is this positive? Is this negative or whatever? What you have to do is look at the reaction diagram and all is revealed. Okay, so let's look at a reaction diagram, okay? So in these energy diagrams, it gives you all of that information about enthalpy, free energy, and entropy, okay? So we can see all of that in a reaction diagram. So don't worry about, those trends and positive and negatives. Learn about how to read a reaction diagram, okay? So in this first reaction diagram, we have our free energy here, and that could be the Gibbs free energy, and a lot of times we'll also say it's equivalent to or approximately equivalent to the enthalpy. Okay. In the start of the reaction, you have your reactants. In this case, we have two reactants. We have two components. We have the thing that's going to react with the substrate, and we have what we call the substrate. The substrate is the organic molecule that you're trying to change its functionality. Okay. So we have reactant and we have the substrate here. Now, they start with a certain amount of energy. That's this right here is the energy those two materials start with. Okay. Now, let's talk about entropy real quick. We had two things on this side, and we're going to generate a new bond and liberate something else right here. We have two components here. So what's our delta S? Okay. In this case, our delta S is probably 0 or very close to it because we started with two things, we ended with two things. Okay, so there's probably not an increase in entropy in the system. Okay, so that's a good way to say, okay, so now it's more about the energy. Okay, it's more about the Gibbs free energy or the enthalpy of the reaction. Okay. So now we have these reactants, and if they don't have enough energy to start to form a new bond, they just stay there. Okay, which means we have to have what we call an activation energy to get it to go to start forming that new product, okay? And we can call that the free energy of activation, which is also the delta G, and that's the double dagger. This is a double dagger right here, okay? That means it's the activation energy required to get to our transition state. A transition state is when your reactant is close enough to your substrate to start forming a new bond. And when it's starting to form this new bond, it's starting to break the old bond, okay? So technically, this transition state is this instantaneous point in time where you're making a bond and breaking a bond at the same time, okay? You can't isolate this. It's very hard to see. There's no analysis for this. You're just going to have to assume it's happening, but you can measure the energy required to do this, and that's our energy of activation. Once you form that new bond, hopefully that new bond is stronger than the old bond. If it's stronger than the old bond, that means it has less potential energy because it's a more stable product. Okay, the more stable it is, the less potential energy it has, or the less free energy it has. So when we look at the difference between the reactant's energy and the product's energy, if the products are below the reactant, we have a change in free energy. We've given off free energy. It is exergonic. Okay. In the case of talking about enthalpy, when it's below this here, we have given off heat, and it's exothermic. So that's how to read a coordinate diagram and understand the free energy, the enthalpy, and the entropy components of it. Okay, but they don't all look like this. So let's look at a different reaction here. Okay, let's look at a different reaction. We have two reactants to start with. We have two products, so our entropy is 0. Okay, we have the potential energy or the Gibbs free energy of the products are higher than the starting materials. Okay, and look at our activation energy. We have to put so much energy into this system because number one, we have to get to this transition state. Number two, we have to put all this energy into the products that we are going to end up making our products have more potential energy. So we have to push energy into the system. And this is what we call endergonic or endothermic, where it takes energy to form these products. And we can do this. It's not very common, but by doing special techniques, you can see that you can get these products to have higher energy. And if you think about it, these reactants are more stable than these reactants, meaning you can make very reactive chemicals by doing special conditions where you have a whole bunch of energy dumping into the system, and you're making these high energy molecules. Okay, so when we see that change, that positive change in Gibbs free energy, we are absorbing energy and making products with more potential energy. Questions on energy diagrams? Okay, so we can do the talk about thermodynamics. How we're going to use it in this class is all about this reaction diagram, okay? So you can see that you have a negative Gibbs free energy because it's less than, the products are less than the starting mole. We have a positive free energy because the products are higher in energy than the reactants. We have our activation energy, which is the energy required to hit that transition state. Okay. All right, so everything we need to know about whether this reaction is spontaneous or not is written down on here. These reactions tend to be spontaneous, and these reactions are not spontaneous. Okay, so that entire slide before this is explained in these two diagrams. Okay, questions? All right, let's move on to what an actual reaction would look like in this energy diagram. Okay. So in this case, we're going to use potential energy right here. And when we're talking about potential energy instead of free energy, we typically look at delta H, or change in enthalpy, okay? But it's the same thing. If the starting material is higher in energy than the products, you are going to give off heat, and you're going to have an exothermic reaction, okay? And this number is negative because it is below the starting materials, okay? So we know just from looking at the diagram that we have an exothermic reaction, and it's probably going to go spontaneously. But it has to have a little bit of energy to make it go, and that's our activation energy now, okay? That's that would occasionally called AE or AEC, activation energy. Okay. Now, let's talk about our reactants here. In this case, our reactant has a negative charge. This negative charge is going to create our new sigma bond. And so those are the electrons that are going to start to form that new bond. Okay. And then we have a sigma bond between the carbon and the bromine here. Those electrons are going to leave with the bromine after we hit the transition state. So now, to get to the transition state, we have to get the two reactants with enough energy and in close proximity to each other to form our transition state. Notice the one coming in has to be 180 degrees from the one leaving, okay? So we have to have enough energy for one to have enough to have them moving around, have enough collisions to have them come in at the right angle, and only when they come in at the right angle can we transition from making this new bond and breaking this old bond to form our products. Notice the driving force for this. If this has more potential energy than this, that means the new bond you're forming is more stable. Okay. If the new bond you're forming is more stable, that's your driving force. You're trying to get to a more stable compound. All right. So this is if we only have that one-step reaction. We're forming a bond and breaking a bond at the exact same time. Okay. Questions on that? Okay. All right. So if we have two steps, our reaction diagram is going to look a little different. Okay. So in that two-step reaction, we have to form what we call an intermediate. Okay. An intermediate is different than the transition state, okay? Transition state is this mythical thing that happens instantaneously. You're bond breaking and bond forming at the same time, or in this case, we're just bond breaking or bond forming. It's that instantaneous point in time where the bond is and then is not, okay? The intermediate, however, is a compound, although highly reactive. It is a highly reactive compound that can be isolated and can be seen by spectroscopy or some other method, okay? So this intermediate actually exists, okay? So Let's start with this reaction here. In this reaction here, we're going to start with some potential energy. We're going to add our activation energy for our first transition state. In our first transition state, we're going to do that bond breaking. Okay. When we do that bond breaking, the electrons are going to go away with the more electronegative atom, in this case bromine, giving us a carbocation and a bromide ion. Okay. Notice the energy of this intermediate is higher than the starting materials. Okay. It took energy to create that higher energy intermediate. Okay. And so it has more potential energy and it took heat to get there, but it's now really reactive. And so because it's so reactive, our activation energy for the second step is smaller than the activation energy for our first step because it's more reactive. It's not as stable. It wants to form a new bond. And so it does form its new bond in its second transition state. And then that cascades down to products. And because the products are lower in potential energy than our starting materials, we give off heat. It is exothermic. And our products are more stable than our starting materials. Okay, so that's how to read diagrams to know whether you have a one-step reaction or a two-step reaction. Two-step reactions have two transition states, two activation energies, but only one change in enthalpy. You only measure change of enthalpy at the end of the reaction. You don't measure change of enthalpy in the middle of the reaction, okay? Because it's the thermodynamic, it's where it happens, you measure it at equilibrium, which tends to be at the end of the reaction. All right, questions on two steps. See why this is so exciting? We get to see what the chemistry is doing and we understand why. All right, so now that's thermodynamics, okay? So we're driving everything to make products that have a different amount of potential energy. If you have a lower potential energy than when you started, you give off heat. If you have a higher potential energy than you started with, you had to absorb heat to make that compound, okay? So kinetics is different. Kinetics is all about the speed of the reaction. So we're talking about the potential energy in an equilibrium in the thermodynamics. Now we're talking about speed. Okay. So in this reaction, we're talking about the rate or speed, okay? And we can get a prediction of how fast or slow the reaction is going just by looking at the height of the energy barrier. The higher the energy barrier, the slower the reaction goes because of you have fewer molecules that have that enough energy and speed and collision to get to that rate, to get to that transition state. The lower the barrier, the faster the reaction. So just by comparing two reaction coordinate diagrams, you can predict which one is going to be faster. Okay? And that's all about the kinetics of things. And the way we look at that is, if you are starting from a certain amount of potential energy and you're walking up a mountain, hiking up that mountain, you're going to do it very slowly. You're going to just you're going to take all this energy to get to the top. Once you get to the top, well, this guy's celebrating, but that's probably what I do too. Now it's easy to go down the hill and get down to the products of the reaction. Okay. So in this diagram, our activation energy is getting to the top here. And then where we end up, the energy at which we have where we end up, that is where our change in enthalpy lies, or our delta H. Okay. So, but it's all about, this is our enthalpy component. This is our thermodynamic component. This is controlling our rate. Okay, so these are both exothermic reactions because our products are lower than our starting material. However, we have two different activation energies. We have a lower activation energy and we have an activation energy that's about twice as high. Okay, so if it took 1 kilojoule of energy to get to this transition state, it took 2 kilojoules of energy to get this transition state. And we can predict just from that activation energy that the one here on the left is going to go faster because that lower energy level. Okay. You have more molecules that are available to spin around and hit each other with an appropriate amount of energy, and it goes faster. Okay. But there are some things that affect kinetics. Okay. The first thing that affects kinetics is concentration. And think about that, okay, that makes sense because to get to that transition state, you have to have two molecules there at the same time, right? And so if you have two molecules there at the same time and you have very few of them, it's going to take a long time for them to actually come together and have enough energy. Or if you increase the concentration of the two components, you have more chances for collisions, you have more chances for them to have the right energy, and therefore it gets faster. So increasing concentration increases reaction rate. Does that make sense? The more molecules you have bouncing around, the more likely they are to hit each other in the right way to cause us to cascade into products. Make that more stable product. Okay. The next thing that affects it is temperature. Okay. The reason temperature is important is because when you have a higher temperature, you have molecules moving around faster, which means they diffuse faster. They're more likely to hit each other. They're more likely to have the right amount of energy to make that transition state happen and cascade. And the cool thing is there's a rule of thumb that says if you raise the temperature of a reaction by 10 degrees C, it doubles the rate of reaction. So if a reaction took an hour at 50 degrees and you raised the temperature to 60 degrees, it would only take half an hour. Okay, so that's the dramatic effect that temperature also has on the rate. So let's see, rate is all about the activation energy height, the concentration, and the temperature, right? Well, not exactly. We have some other things it can do. Okay. But the reason temperature is such a big factor and it doubles the rate every 10 degrees is the number of molecules that have enough energy that's above the activation energy. Okay. So in this diagram here, what we're looking at is the weighted average of energy. So this is our energy right here. And it looks like, and this is the number of molecules here. So right here, you know, about 50% or more or less of the molecules have this energy here, right? So all of these molecules have that energy or less. Okay. None of those molecules can react because none of them are above the activation energy. Okay. So let's go to over here. Okay, that's 95% of the molecules, and they all have, you know, that amount of the energy. However, it's still below the activation energy, so none of those molecules can react. Okay, so only this little bit of these few molecules here that have an energy above the activation energy actually react. Okay, so that's let's call that the 50-degree reaction here. And so only these molecules can react, and therefore our rate is whatever it is. Our rate is, let's call it relative is 1. Okay. Now, by raising it 10 degrees to 60 degrees right here, notice the average, so the peak here is higher in energy. But still, all of those molecules, actually let me change the red here, all of these molecules still don't have enough energy to overcome the activation energy. So by the time we get to about 80% of the molecules right here, 80% of the molecules don't have enough energy to do the reaction. However, now 20% of the molecules do. So we have a much bigger area under the curve from that reaction, and therefore it doubles the rate of the reaction. Okay. It's all about the number of molecules that have enough energy that are above the activation energy. 90% of the molecules are not above that, but guess what? You know, 85% are not above it, but 15% are, and they're going to go and they're going to form that transition state, and then it's going to cascade to products. Okay? So, kinetics is all about speed, lower activation energy. We have a concentration effect and a temperature effect. What else do we have? Steric hindrance. Okay. Think about that. If you have a molecule that has 3 large groups on it, and the part that has to leave in our transition state is over here, you have to start to form your new bond in between these 3 big groups to start breaking this bond here. Okay. So if you're trying, you have to come in at this exact right angle, and you're doing random collisions coming at all different angles. So you have very few chances for it to hit at that exact right angle to squeeze in between all of those groups. Now, if we remove 2 of those groups, and so we only have 1 here, now we have a bigger window of attack. So steric interactions if the more sterically hindered the thing is, the bigger the groups are, the slower the reaction, because the fewer times that you can come in exactly at the right angle to get that transition state to form. Okay. And we're going to talk about nucleophiles and electrophiles in a couple slides. Rate is all about activation energy, concentration, temperature, and steric interaction, right? Okay. So let's talk about what we call our rate equation. So if it's about these things, about the temperature, the concentration, everything like that, we need to figure out a way of measuring this, okay? So when we measure this rate, which is the reaction rate constant is K, we have to measure the speed at which the reaction happened and times the concentration of the two components forming that transition state. In this case here, for a substitution reaction, where we have that one step, where we have to form the transition state, we're making and breaking the bond at the same time, we have to include the concentration of the substrate, or the thing that has the carbon on it, and the thing coming in to create that new bond. Both are important because both have to be in that transition state. So our rate law, or what we call it, our rate law is the rate is equal to some constant for that specific reaction times the concentration of the two substrates, which means your rate can be 1 if your rate constant is constant and your concentration of 1 is 1 right here, okay? But if concentration depends on the rate, if we increase the concentration of one of the reactants right here, we're going to double the rate. And if we increase the concentration of both reactants, we're going to quadruple the rate. So that's the importance of this rate law equation, and that's the importance of concentration on the rate of a reaction. Okay, so how does this relate to activation energy? If activation energy is the thing that tells us how fast the reaction goes, how does it relate? Well, we can actually calculate the activation energy from the rate constant, okay? So we can take the rate constant, right, have right here, and it's equal to the pre-exponential factor, which is different for each type of reaction. And then we have the activation energy divided by the gas constant and the temperature in Kelvin. And we are taking it the e to that power. So it's the opposite of natural log, okay? So this is important, right? Our rate constant is equal to our activation energy here. As activation energy gets bigger, this number gets bigger and this number gets smaller because we have a negative. As this number gets smaller, and look, if temperature gets higher, that number gets smaller and our rate goes up. Okay. So if you're really like the math there, that's kind of why activation energy is directly correlated to our rate and our rate constant, and the fact that temperature as it increases rate, and as activation energy decreases, it increases our rate. All right, questions on that? And again, no, we're not going to calculate this. I just want to show you that how they're related. So the other thing that we can change the rate on something is to use a catalyst. Okay. So in the case of a catalyst, instead of going through that single transition state where you had to have everything be in the right energy in the right position, you actually form intermediate steps that are lower in energy. For example, instead of having the one component come and start bond forming and bond breaking, what we could do is we could actually have it react with something else that's easier to react with. And then that reacts again, and then that reacts again. And all of these reactions have very low activation energies. But the net result is you end up at the same product. Okay. So a catalyst, what a catalyst does is lowers that activation energy and actually changes the mechanism. It changes the mechanism because you're doing different things because you've lowered the activation energy. Let's say instead of breaking a bond to form this, you actually make a new bond and then you transition it to another bond, then you transition it to another bond, and then that comes to your product. So you've actually changed the reaction pathway. And when you change the reaction pathway, you can change the activation energy. Okay. So kinetics is all about rate. How fast, how fast, how fast. All right. So, so when we think about things that are endothermic or exothermic, we actually have a way of looking at it from the fact of how close the transition state looks to the starting materials or the products. Okay, so in the case of an SN2 reaction, well, in the case of the first reaction here in red on the left, we're going to be bond breaking and bond forming at the same time. However, because we're an exothermic reaction, the products have much less energy than the starting materials, which means the transition state is going to look more like the starting materials because we're giving off a whole bunch of energy in the end. So it's going to look more like the starting materials. In the opposite of that, in an endothermic reaction where the products have higher energy than that, then that means that the product has higher energy, which means the bond that it's breaking is weaker than the bond that it's forming. So if the bond breaking is weaker than the bond it's forming, we're going to look closer, more like the product in our transition state than our reactant. Okay. So in the case of exothermic reactions, the transition state looks more like starting materials. In the case of endothermic reactions, the transition state looks more like products. Okay, so that's what we call the Hammond postulate. And it's another way of looking at those reaction diagrams, looking for energy and looking for changes in bond strength and bond energy. Okay, so kinetics and thermodynamics can be competing in a reaction. Okay, and so in the case of kinetics, we're all about the rate. We're all about that activation energy and where the what the concentration of the reactants are. Okay. When we're talking about thermodynamics, we're related to basically in equilibrium, you are going to form the most stable product possible. Okay, so kinetics, it's fast. You don't necessarily form the most stable product. Thermodynamics is in equilibrium and therefore will continue to go back and forth until the most stable compound is formed. Okay, so it's all related to that change in free energy or that change in enthalpy. Okay, so if they're competing, how can we tell the difference? Okay, well, let's look at our energy diagram. Okay, so let's say we have our two components here, and at our activation energy 1, let's heat it up to 50 degrees. And when we heat it up to 50 degrees, it only has enough energy to hit this activation transition state, not this transition state. And it produces compounds C and D. Okay, so the first thing we want to look at here is that this activation energy is smaller than this activation energy. So which one's faster? Activation energy 1 or activation energy 2? Activation energy 1, that's correct. Because it's a smaller activation energy, it goes faster. Okay, so that means this is the kinetic product right here, because this is the faster activation energy, and so these are the kinetic product. Let's add more heat and get it to a different transition state. So we've added more heat, we have a higher activation energy to get to a different transition state. Because it's a different transition state, we produce different products. Let me change. Because we have a higher transition state, we produce different products. Now note, this is slower because it took more energy for that thing. And what's the other thing that happened? Our products are less stable. We went to a different transition state, which gave us different products that are less stable. So in this case, our green line here is kinetically favored because it has the lower activation energy, and thermodynamically favored because it made the more stable product. Okay, which means the red one here is kinetically not favored and thermodynamically not favored. Okay, so if you ran this reaction, you would get more of this set of products right here than the EF products because it's kinetically favored and thermodynamically favored. So is there times where they can compete? Yes, there is. Okay, so let's look at a different set here. And let's look at our red line here. We have our activation energy here that's lower. So that means the red line is our faster reaction. Okay. Now, our bluish green line here has a higher activation energy. So that's a different transition state. But the products are more thermodynamically stable because they have a greater change in that delta H. Okay. So in this case, the blue line is thermodynamically favored, but kinetically not favored. The other reaction is faster, but this reaction creates more stable products. But the red line here is kinetically favored, but thermodynamically not favored because the products are not as stable as with the C and D products. Okay. So we have a competition between kinetics and thermodynamics in this particular state. Okay. So just theoretically, how can we make sure that we form the more thermodynamic product? I think you just add a little more heat so more of your molecules can enter your higher activation energy transition state. If you have more energy hitting your higher activation energy transition state, you should get the more thermodynamic product. Okay. So it also tells us that if we heat the reaction up, we have the possibility of forming products we don't want. Because if we heat it up too much energy above the transition state we're trying to hit, if we go much higher than this one, if we go much higher than this, we're going to start to hit another thing. And so we're going to get different products. So that raising the temperature can be good for you by speeding things up, but it can be bad for you by changing the products because of the thermodynamics. Okay. Questions on that? Okay, so we have a competition between the kinetics and thermodynamics. Okay. So the rate of formation of the most stable product will be faster than the rate of the formation of less stable product because the most stable product follows the pathway that has more stable, lower energy transition. So if you have a kinetically and thermodynamically controlled system, you are going to have fewer side products because it's faster and more stable. Okay, so it's looking for things that have the lower activation energy and the most release of heat. Gives you your best reaction conditions. All right, so what that means is that by not heating it up too much, such that you never have enough energy to go to your higher transition state, your higher activation energy, you can make sure that you have kinetic control, okay? Because the lower transition state is faster, right? And if you keep it at lower temperature so you don't go to that second transition state, you will form you can form less stable products, okay? Now, when you do this at that lower temperature and you're controlling that rate, you're under kinetic control. Now, it's kinetic control because the products are less stable than the system, okay? So it's faster, but less stable. That's kinetic control. But by raising the temperature, we can go to thermodynamic control, okay? Even though the other products were formed faster, the products for C and D were more stable. And so by heating that up at a higher temperature, making it go to that other transition state, you can form the more thermodynamic product, and that's called thermodynamic control. Okay, so you need to know which kind of ones you want. You can use kinetic control to get the less stable products. You can use thermodynamic control to get more stable products. Questions on that? Okay, come on, there's 32 of you. Somebody's got to have a question. All right. All right, so now you saw the word nucleophile electrophile in the previous slides there. And so now I'm going to talk about that in detail. Okay. So, and we're going to go back to our chapter on Lewis acids and Lewis bases and give them a new name. Okay. Our Lewis bases are nucleophiles. Okay. Nucleophiles are an electron-rich atom capable of donating a pair of electrons to form a new sigma bond. Nucleophiles are an electron-rich atom capable of donating a pair of electrons to form a new sigma bond. So that means Lewis bases are nucleophiles. And we can think about that as anything with a negative charge, anything with lone pairs, or anything with a double bond are going to be nucleophiles, okay? Because they have electrons to share. Okay. Which means, in contrast, electrophiles must be the opposite, right? The electrophile must be an electron deficient atom capable of accepting electron pair to form a new sigma bond, which means Lewis acids are electrophiles. They're willing to accept that lone pair. And when we think about that, we think about alkyl halides, electron deficient atoms, and positively charged species. But why are alkyl halides electrophiles? Bond polarity, okay? So let's look at some common electrophiles and nucleophilic centers. Okay, so in the first one here, we have 4 bonds to carbon, so we have a neutral species. We don't have any lone pairs, okay? Why is it a nucleophile? Bond polarity, okay? So let's look at this right here. We have a carbon and a lithium. The carbon is more electrophilic, has a higher nucleophilicity, right? It's closer to fluorine, okay? Because of that, it's going to pull electron density away from the lithium, which has a lower electron negativity. So what that means is that there's going to be a partially negative charge on carbon and a partially positive charge here. Okay, so this is partially negative, which makes it a nucleophilic site, meaning a nucleophile can come in and attack that partially negative carbon. Okay. The other way of looking at nucleophiles is anything with a lone pair. That lone pair is ready to reach out and form a new bond. And we see that a lot in this system. Like when we protonate water, it is reaching out with that lone pair to have it there. And so that lone pair is the nucleophilic site on there. Okay. But what about the pi bond? Well, remember the pi bond is above and below the plane of the 2 nuclei. So there's kind of out there in space. Because they're out there in space, that pair of electrons to make that pi bond is reactive and acts as a nucleophilic site. It's ready to share those and change hybridization and share those electrons to form a new bond. So all of our nucleophiles have that in common. It's willing to share some pair of electrons on it because of it's partially negative, fully negative, or has a lone pair available to play with, or has a pi bond. Okay, so what do electrophiles look like? Well, it's kind of the opposite, right? So if we look at things like this compound here, it's a neutral compound, but it has a polar bond. And the fluorine is trying to extract all the electrons it can, meaning the carbon is partially positive. That means we can have a negative charge come in here and attack that partially positive carbon. So that's our electrophilic site, okay? The other way to do it is to have a full positive charge. In this case, we're talking about a carbocation, and we'll talk about that in a little more detail here. We have a full positive charge, making it ready to accept a pair of electrons whenever possible, okay? And in this case, we have an electron deficient atom. Boron is next to carbon, so it's less electrophilic than carbon is. And because it didn't fill its octet, it's actually an electron deficient atom. And so it's willing to act as our accepting of electrons. It's willing to act as our Lewis acid. Okay. So let's look at those terms again. Lewis acids are electrophiles. Lewis bases are nucleophiles. Nucleophiles have lone pairs, negative charges, or double bonds, or very polar bonds. Electrophiles are ready to accept those. They have polar bonds with a good leading group, a good negative leading group. they have electron deficient atoms, or they have positive charges. All right, questions on nucleophile and electrophile? Because from this point on, we are going to be using the term nucleophile and electrophile a lot. And so make sure you have that kind of in your head. And it always helps to, when you look at a new reaction, you don't know what's happening, look for bond polarity, figure out which one's the nucleophile and which one's the electrophile. A lot of times, about 85% of the reactions we do have some kind of nucleophilic electrophilic interaction or a Lewis acid base interaction. Okay, so the next step is to use a stepwise progression of what's happening in a reaction. And we call that a mechanism, okay? And when we want to do that stepwise understanding of what's happening in a reaction, we push electrons around using arrows, okay? So in the case of an arrow with 2 barbs on it, that means you're moving a pair of electrons, okay? If you have a single barbed arrow, that means you're just moving 1 electron. So for the next few chapters, always put 2 barbs on your arrows showing that which electrons are going to which center, okay? So in this example here, we have our nucleophile, okay? How do you know it's a nucleophile? It has lone pairs, it has a negative charge. Nucleophile, okay? It's a really good sign that it's a nucleophile. Okay, we have this as our electrophile. It has a positive charge. That's a pretty good sign. It's an electrophile. Okay, so what's going to happen? We're going to react that nucleophile with that electrophile to form a new sigma bond. Okay, where do the electrons come from? The electrons are always going to come from the nucleophile. So in this case, we're going to take the lone pair off of this bromine with a negative charge. We're going to take both electrons and form a new sigma bond to give us our new species. Okay. So this is what we call a single-step nucleophilic attack. We already have 2 charged species, and we're going to a neutral species by generating that new sigma bond. Okay. Now, notice that these electrons are highlighted in red to show you those 2 electrons form that new sigma bond. It's not 1 electron from one and 1 electron from the other. Both of those electrons came from the bromine. Okay, so if that's a 1-step nucleophilic reaction, what would a 2-step nucleophilic reaction look like? Okay, well, in a 2-step nucleophilic reaction, you typically would start with a charged species and end with a charged species that then has to do something else to get back to neutral. It has to lose a group or something. So let's look at that. And so the nucleophile, easy to see, we have a negative charge and we have lone pairs, so nucleophile, that's easy. But why is that an electrophile? Oh, wait. We have a polar bond between the carbon and the oxygen, where the oxygen is pulling electron density toward the oxygen because it's more electronegative. And so that means that there's a partially positive charge on carbon and a partially negative charge on the oxygen. So because we have that partially positive charge because of bond polarity, we now have an electrophilic center. Okay, so we have that partially positive charge. That's where we're going to do the attack. Now, the reason this is 2-step is that we have the electrons coming in from the nucleophile to that center, but we can't have 5 bonds to carbon. So we have to break a bond, okay? And the least stable bond for this is the pi bond. The sigma bonds are more stable than pi bonds, which means we're going to break the pi bond to give us a total of 4 bonds to carbon and never more. And we end up moving those electrons on the more electronegative atom, in this case, oxygen. So if you wonder where the electrons are going to go, are the electrons going to go over here? No, no, you're going to put them on the more electronegative atom, in this case, oxygen. Okay. And that creates our new charged species. Now, the next thing that's going to happen is you've got to somehow get rid of this charged species. You can add a proton to it or something like that, and that would be the next step. Okay, so, but you'll never form 5 bonds to carbon. You'll never have 10 electrons around carbon. So make sure that when electrons come in on something that already has 4 bonds, you have to break some bond, usually a pi bond or a less stable sigma bond. Okay. All right, questions on that? And by the way, thank you for being live on this Pre-spring break holiday. All right. So there's also a couple ways to do this. Remember, one of the things we can do is we can actually break a bond, okay? And the way we break a bond is we figure out where the electrons are going to go. The electrons are going to go with the more electronegative atom, okay? So in the case of this bromine carbon bond, the electrons are going to go with the bromide, okay? Is the two-step referring to a bond breaking and bond making at the same time? Yes. All right, so in this case here, we're actually going from a neutral molecule to two reactive species. But again, we have to figure out where the electrons are going to go. The electrons are always going to go with the more electronegative atom, meaning the bromide is going to create that. And now this is a nucleophile, okay? This is a neutral species. This was the electrophilic center. This is the nucleophilic side of the molecule, but we're breaking it off to make a full negative charge and a full positive charge. Okay, so remember, when we take both electrons away, we call that heterolytic cleavage. Okay. In this case, we're forming a carbocation, a cation on carbon, and a nice stable bromide ion. Okay, so we can also do this with a proton transfer or hydrogen transfer. Okay. And the way we're going to do that is like we did with the acid-base reactions when we're looking at Bronsted-Lowry, in where we have some electrons from a lone pair on something are going to reach out and create a new sigma bond. In that process, we have a bond here. We have oxygen as the more electronegative atom, so it's going to take the electrons. So the electrons are that the oxygen on the base have here is going to form that new sigma bond. And when it does that, we end up with a positive charge on oxygen. And those electrons are the ones that form the new sigma bond. The electrons that were forming the bond to make the hydronium ion go to the more electronegative atom always. And so they stay on the oxygen. So you can always look for where the electrons are going to go by saying which atom's more electronegative and which bond is the easiest bond to break. So it doesn't have to be with hydronium ion. We can actually protonate alcohols as well to form oxonium ions. And we use those a lot in the first step in catalytic reactions. And so we'll do the exact same thing. We're going to have something come in and act as a base. In this case, it has a full negative charge. Those electrons from that base are going to reach out and form a new sigma bond with that hydrogen. And that hydrogen is going to leave those electrons with the more electronegative atom. Okay? So we end up with a neutral alcohol species and a neutral water species. So that is using arrows and knowing where the electrons flow in the transfer of a proton. Okay. All right. So I said we're going to talk about carbocations. Carbocations are kind of important because we use it as a useful intermediate. In fact, a lot of times when you take two-step or two humps in a reaction diagram, the intermediates, a lot of times it's a carbocation. And so we're going to talk a lot about carbocations and carbocation stability. Okay. So the first thing is we can classify carbocations by how many other carbons are attached to the carbon that has the positive charge. If there's one other carbon or other thing, or typically it's carbon, that's going to be what we call a primary carbocation. If there's two carbons attached to the carbon that has the positive charge, we call that a secondary carbocation. And if there's three carbons attached to the carbon with positive charge, we have tertiary carbocation. Okay, you can't have a quaternary because that's 4 sigma bonds and it's happy. There's no positive charge. So it's primary, secondary, and tertiary. The only other condition we have is methyl. Okay, methyl has no other carbons on it, and so that's why we call that the methyl, primary, secondary, and tertiary. So the number of substituents directly bonded to that positively charged carbon controls its stability. And we see that the least stable is that methyl cation. Next is the primary right here, only one carbon attached to it. This is our primary, this is our secondary, and this is our tertiary. Okay. So let's step back and think about the structure of this carbocation. Okay. So with the structure of this carbocation, what we've done is we have changed hybridization. Okay. We've gone from an sp sp3 hybridized carbon to an sp2 hybridized carbon. But where's the positive charge? Okay, so let's draw a tertiary carbocation here. We're going to have a carbon here, a carbon here, a carbon here, and a carbon here. And it's trigonal planar because it's sp2 hybridized. Okay, so that's 120 degrees, flat plane. Okay. Where's positive charge? Wait, hold it. That's sp2 hybridized. Where's the other S? Where's the other P? The other P is above and below the plane of that trigonal planar 3 carbons there. And it's empty. So there's no electrons in that orbital, but it does exist and it has a positive charge. Okay, so that tells us something about why these carbocations are, how they're going to react, but it also gives us an idea of where that positive charge lies on that system. Okay, so our stability has everything to do with both the carbons attached to these, to the center, as well as the hydrogens attached to the carbon here. Okay, so there's 2 effects that help stabilize that carbocation. Okay. So the first effect is what we call the inductive effect. Okay, so the more things you have attached to that carbocation that can donate electron density to that positive charge, the more stable it is. Okay, that's why the tertiary is more stable, because you have a carbon with 3 other carbons attached to it, which means they can each donate a little bit of their electron density to the system. When you have carbon with no carbons on it right here, those hydrogens only have only have 1 electron. They can't donate any more electron density. And so that makes this the least stable. But just by adding a single carbon here, we can increase the stability a little bit because the carbon next to it can donate. And if we add another carbon, we can get a second donation from the second carbon. And a third carbon gives us our most stable carbocation because it's getting electrons donated from all of those things. That's the inductive effect. So that's why tertiary carbocations are stable, by the fact that it's pulling electron density in from there. So it's less positive. Instead of being 100% positive charge in that methyl, right here, 100% positive charge, it's spreading, it's getting electron density for, so maybe it only has a 75% positive charge, or it has a less amount of positive charge because part of that is being inductively pulled in by those other carbons. Okay. Now, the second thing is hyperconjugation. Hyperconjugation is a through space interaction, okay? So we can think of this hydrogen having this electron cloud around it, and this hydrogen having an electron cloud around it, and this hydrogen having an electron cloud. One of those hydrogens is possibly going to be able to line up with that p orbital above and below the plane. And so it can donate through space to the p orbital. And then this one's going to have a hydrogen over here. It can donate through space to the p orbital. And this one's going to have a hydrogen somewhere, and it can donate through space to that p orbital. Okay, so that through space interaction is what we call hyperconjugation. And so that's another reason why the tertiary carbocations are more stable. It's got 3 carbons to inductively draw through and 3 possible hydrogens to do hyperconjugation. Okay, so does that make sense that tertiaries are more stable than secondaries or primaries? Okay, all right, I got just about 5 minutes. Okay, so if we think about it right here, because the hydrogens here cannot donate any of their, that's 100% of the charge is staying on that carbon. It cannot get anything else. By having a little bit of inductive effect, we can get like maybe 5% or so. So this is only 95% of the positive charge. This is a relative number. It's not an absolute number. I'm just giving you an idea that by that inductive effect and a little bit of a conjugation effect. Okay, yeah, let me just finish this slide and then you can do the slide thing. We forgot to do that at the beginning, didn't we? Okay. In the case of 2 right here, we have the 2 different inductive effects plus 2 possible hyperconjugation effects, making it more stable. So maybe this is 85%. And by the time we get 3, we have 3 different inductions, 3 different hyperconjugations, And that's 75% of the positive charge, making it much more stable. Okay, so we got about 5 minutes left, but Sheila would like to talk to you about recruitment for Slack here. So what I'm going to do is I'm going to stop sharing and allow Sheila to share her screen.
Oh, it was just kind of just a speech to
okay.
Talk about it.
Right.
But good morning, everybody. I know that, you know, it's the end, but good morning anyway. It's almost, well, I guess it is still morning. I just wanted to let you guys know that Slack is always hiring. So you could be like an SI, just like me, or a lab assistant or a lab tutor. They also have other positions available, which you can see on the Texas State website if you're interested. To qualify, you would have to have a 3.0 cumulative GPA and receive an A for the class that you're applying for. And so far, this is my first semester being an SI, and I actually really enjoy it. It's nice to communicate with Professor Dr. Irvin and, you know, get to know him a little bit and know what he wants me to tell you guys. And I especially love whenever you guys start to connect things. It's a really good feeling when everything kind of connects. So if you're interested, definitely check out the Slack website on Texas State website, and you guys can become an SI next semester. And that's pretty much it. I didn't have, you know, super long something, but.
Okay. And another advantage of working for Slack or working for a professor as an SI is they get to know you better, and they can write better letters of recommendation when you need them. So, you know, it's one of those resume builders, but it's also a relationship builder, and it's building your network for wherever you're going to end up. So that is kind of really good. If you have the time or want a little bit of pay on the side, then that is definitely a good thing to do. Plus, what I think Sheila has learned is by taking the class once, you learn some things, but by trying to teach the same topic, you learn it better. You will know the topic better by the time you, after you start to try to teach it, try to explain it in your own words, you're going to understand the topic better.
That's very, very true. And to answer the question that's in the chat, let me pull that up really quick. I was supposed to write that down and forgot, so thank you for reminding me. So let me find it. So early SI application deadline is going to be Friday, April 2nd. And then new SI hiring interview conference will be April 17th. So keep those in mind. And then also for my Sunday people, we won't have session this Sunday, but we'll have session the following Sunday after spring break. You're welcome.
Slack does hire tutors and other positions almost all the time. So I would just go to the website. It's the SI that has this training session associated with it, and they have to begin at the beginning of the semester.
Yeah.
That for the summer session? Is that for summer sessions, the training that's coming up?
I'm not sure if they're going to be putting new SIs in summer. Usually it's going to be returners that do summer sessions.
Okay, cool.
But yeah, cool.
So in the SI training, you also get a whole bunch of training about how to use Zoom. Well, you might be back real in time, but they teach you how to come up with a lesson plan, do activities, do group-to-group learning, do individual learning. So that you actually get some really cool skills from the training. So if you really like the topic and like helping people or like teaching, I highly recommend the SI program. So
that's pretty cool.
So we're right here at 9:20. So that's when we're supposed to end, I believe. And so what I'm going to do is I'm going to go ahead and stop recording. And if you have questions, stay behind and I'll answer anything you have. Have a safe spring break, wear a mask, come back to us safely and healthy, please.